Hello everyone, welcome back to another class on regeneration biology. And in today's class, we will learn about different aspects of organ culture. In the previous class, we have learned about how different scaffolds or how different materials can be used for culturing them or growing them, etc. We will also see some challenges in the next class. But we will try to learn about different aspects of organ culture, in the sense what are the pros and cons, what is the best and what is non-best, or what is not so good approaches for organ culture. So we can understand what are the possible vista of matrix production. Artificial matrices are used extensively due to their various biological properties, but they come with their own challenges. But now people have shifted into using natural ECMs or natural matrices, which is the same matrix what an organ had. Say for example, if you want a liver, use the matrix from liver only. If you want a kidney, you use the matrix from kidney only. So that approach, that is getting rid of cells from an organ and retain the matrix, it can be from anywhere. It can be from an animal, it can be from another cadaver, it can be from some other sources. A donor, of course, you can't use it because you cannot take an intact organ from a donor just for the sake of getting the matrix. So if it is mainly from a cadaver, if it is not going to be, or that organ is not going to be used, or it is already dead, it is crossed its time of transplantation, then that organ can be used for the matrix. So that is called decellularized extracellular matrix for organoid and engineered organ culture. So the repair and regeneration of tissues and organs using engineered biomaterials has attracted great interest in tissue engineering and regenerative medicine. People have been doing that. But recent advances in organoids and engineered organs technologies have enabled lots of researchers to generate 3D tissue that recapitulate the structural and functional characteristics of native organs as it is. Say your kidney is having, say, 5.2 centimeter in diameter or length, you can make exactly that, not 5.3 or not 5.1, exactly 5.2, opening up new avenues in regenerative medicine. Such an approach has cleared a lot of hurdles, or allowed us to jump lots of troubles, or get across the problems. So the matrix is one of the most important aspects for improving organoids and engineered organ construction. We know matrix is the backbone of an organ. However, the clinical application of these techniques remained a big challenge because of the current commercial matrix does not represent the complexity of the native microenvironment. It is not because of the bioacceptability, biodegradability, etc. It is not able to, we are not able to mimic the complexity of the matrix, which in turn is because of the complexity of the organ itself. It limits the optimal regenerative capacity. Decellularized extracellular matrix, it is short form, it is called dECM. ECM we all know. dECM is decellularized extracellular matrix, is expected to maintain key native matrix molecules that is believed to hold enormous potential for regenerative medicine applications. dECM can be used as a matrix for improving organoid and engineered organ construction. In the sense, you can get rid of the cells from an organ, what remains is nothing but ECM. So let us quickly see a overview of the organ culture. As you can see in this picture, the repair and replacement of damaged tissue or organs are driving an expanding need worldwide. A lot of people are in need of organs. However, there is a critical shortage of organs available for transplantation, and the post-transplant immunological rejection still remains a significant concern despite having immunosuppressant drugs. In the United States alone, one country where all these details are documented, the annual expenditure for disease related to tissue defects and organ failure exceeds 400 billion. 1000 million is 1 billion, so 400 billion is per annum. You can see here, you have an organ, let it be lungs, liver, stomach, kidney. What you can do is, you can make all these organs. If you start with a decellularized, you take a tissue or organ and decellularize and recellularize using the patient derived cells, and you end up getting either organoids or organ, depending upon what organ you are trying to make it. Sometimes organoid is enough, it will automatically mature into organ itself. For liver, etc., you don't need a intact full-fledged liver. A small piece is enough. If you make the connections, everything fine, that liver will grow. And some organs such as a stomach, etc., you need full-fledged organs. A kidney, you need a full-fledged kidney. So organoids or organs can be made from this decellularized matrix. So why ECM? What is so-called? We have discussed about ECM, and dECM is a new concept right now. ECM plays a critical role in cell signaling, function, phenotype, and morphology, providing a beneficial microenvironment for cellular homeostasis, growth, tissue formation, and repair. It is not a structural support, although we compare to that of beams and pillars of a building is equivalent to a matrix. But beams and pillars are not providing you energy. Beams and pillars are not giving you any nutrition. But these matrix proteins provide nutrition and a favorable environment. They will cells feel home when the matrix is present. So each tissue or organ has its own unique ECM. Lung has a different ECM. Liver has a different ECM. Kidney has got a different ECM. And the interaction between cells and the ECM are crucial in regulating cells' behavior, function, and fate. So everything decides, everything is very crucial and detrimental when it comes to ECM cell interaction. Due to the complex biological properties and 3D ultrastructure of native ECM, replicating them using traditional manufacturing methods and biomaterials is often challenging. Hence, the ECM what you need for your research or an organ production can come from a existing organ itself, and you make dECM out of that organ. Now, why dECM? Decellularized extracellular matrix materials refer to biomaterials formed by removing immunogenic cellular components. You may wonder why cells have to be removed. First of all, the cells are not from this person. If the cells were from the same person, then there won't be any immunorejection. Because a liver cell between X person and Y person, there is no main difference. But the liver cell from person X, when put into Y, it is a foreign body. His Y person's foreign body will reject it. That is why we don't want that cell. But whereas matrix, that is not an issue, because matrix doesn't have the MHC complex protein present on the surface of those cells, which is unique to individual humans. So immunogenic cellular components is what you are trying to get rid of from human, or if it is from another animal. Say you took the kidney from the pig, everything is fine, but the pig cells you don't want, although pig kidney is working perfectly fine. So animal organs and tissues always cause severe immunological rejection. But if you decellularize it, then that matrix is not an serious antigenic molecule in your body. dECM minimizes changes to ultrastructure and composition and provides an excellent 3D microenvironment for subsequent cell seeding, opening new avenues for tissue engineering. So they because of the complex and unique nature of ECM meshwork, then when you seed the cells, they will recapitulate the same structure back as it was needed or as it was there in the original organ itself. In clinical practice, dECM is progressively being adopted to support tissue repair and transplantation therapies. We will see some examples also. Let us see some examples how and where we stand as of now. Various commercially available dECM products have been developed, including Allodum, it's a registered trademark company, and Graft Jacket, another company, which are derived from human dermis and is used for repairing skin wounds and tendon and ligament injuries. Say you got some serious injury, and we know if you allow it to heal it, it will be filled with fibroblast. You may have seen surgical suture. You can, even after 20 years, you can see, oh, there was a surgical suture. That mark will stay because of the fibrosis. Because you damaged not just the epidermis, but you damaged the dermis. The moment dermis is damaged, the basement membrane is affected. Hence, you will get the fibrosis or the fibroblast migration. But now imagine a situation, you have the ECM of the skin and you are putting on top of that wound area. Now the cells from the surrounding will migrate on this ECM and it will restore the normally looking skin. So you have no way of knowing, was there a cut, was there an injury. So these are all very easily doable thing. That is why allodum, graft jacket, etc. have come into picture. And they are also used for several other wounds of the tendon, ligament, etc., which normally sports person gets it. Another company, Oasis, sourced from porcine small intestinal submucosa, is utilized for skin wound healing. That is from a pig. While Prima Plus and Cardiocell, another two companies derived from porcine and bovine cardiac tissues, are employed in cardiac valve repairs. The emergence of these products underscores the versatility and the potential of dECM based biomaterials for clinical applications. So we can use them for fixing any of the damaged part or organ itself from these commercially available sources. Currently, where we stand is the tissue engineering materials derived from dECM have been widely applied in the fabrication of engineered tissue and organ-like constructs, including gastrointestinal tract, kidneys, liver, lungs, pancreas, uterus, bone, cartilage, heart, skin, brain, esophagus, and oral cavity, and so on and so forth. Many other examples are there. So pretty much every organ, if the damage is moderate, you can take help of these commercial firms and you fix it. Now let us see a little bit about the organoids, what is their history and how it has come up, etc. Single cells or small clusters of cells proliferate and reorganize to form complex structured cellular assemblies that mimic the functional attributes of specific organ termed organoids. Organoids are nothing but organs itself, but they are miniature version. Like you may have seen in some house, you will have a huge guitar's miniature version or tabla's miniature version, something like that. But it is, you imagine if they are functional also. Sometimes some miniature version will be functional also. It is just smaller in size. The study of organoids traces back as early as 20th century. In 1907, Wilson demonstrated that dissociated sponge cells are capable of self-organizing and regenerating entire organisms itself. Sponge, the animal. The foundational work for organoid technology was laid in 1981 when Evans and Martin independently isolated pluripotent stem cell lines from the mouse embryos, and with Martin naming them embryonic stem cells. By 1998, Johns et al. Had successfully isolated and cultured embryonic stem cell lines from human blastocysts, expanding the possibilities of using stem cells to culture organoids. Significant advancements were made in the year 2000, 2009, etc. When Professor Hans Clevers coined the term organoid, and he cultivated the first intestinal organoid from LGR5 plus stem cells derived from mouse intestine. He used a mouse model. Recent years have seen several rapid developments in organoid research, including Menjan's generation of self-organized cardiac organoids from human pluripotent stem cells. In 2021, Clevers et al. Showed the establishment of human fetal hepatocyte organoid model. So we are developing the organoid era like anything. Significant advancements in reproductive system of organoids were made from 2018 to 2022. So this is a historical overview of organoid development. I will not go each and every section. You can read about it. In 1907 till 2022, if you see, there is a rapid development in the field. You can see in each year some or the other development has happened. You can go through it. Those who are interested can read this article as well. Decellularization of the extracellular matrix. Although we are telling dECM, how easy or how difficult it is, we should try to understand that. dECM is a promising natural biomaterial prepared from human or animal tissues or from organs itself through decellularization. Idea is very simple, no complexity to understand. Take a liver, let it be from human cadaver or maybe from an animal, get rid of the cells, retain the liver as it is, just remove the cells. That is a simple concept. dECM retains the 3D structure and biological properties of ECM, exhibiting bioactivity, biocompatibility and non-immunogenicity. That is the most critical part, is not immunogenic. It preserves numerous cell growth factors such as fibroblast growth factor, transforming growth factor and hepatocyte growth factor if it is liver, which can enhance seeded cell growth, migration, proliferation, differentiation and angiogenesis. We discussed about it. If you made a properly functioning tissue in a tissue culture but it doesn't have blood vessels inside, then how the host will supply nutrition, oxygen and glucose to those tissues? Impossible. So angiogenesis, the blood vasculature, is more important than the tissue itself. Otherwise, it will be like operation successful, patient dead. You don't want such a scenario. Oh, beautiful kidney, I made it, but it doesn't have blood vessels. So it will look like a toy model, like we saw art, like worry doll and all we saw in the previous class. It will be like that. It doesn't have too much of sense. This real-time interaction with the seeded cells can reshape the structure of tissues and organs, playing a crucial role in the tissue and organ regeneration and its functional repair. Therefore, various scaffolds materials based on dECM have garnered increasing attention in recent years because it works. Hence, people will go after it. The origin of ECM. ECM can be derived from three primary sources: human tissues, cell cultures and animal tissues. This we know. These are all the sources of ECM. ECM from human sources significantly reduces the risk of immune rejection associated with xenogenic ECM. Although we say this dECM, ECM doesn't have immunogenicity, etc. But if it is from a completely different animal, there is a possibility that ECM protein itself can have some antigenic material. There is a possibility, such as the response to alpha-gal epitopes. Sometimes some animals can have some unique epitopes in their ECM proteins, which can be immunogenic. Hence, your organ can get rejected. Human-derived ECM best mimics the structural and functional properties of native tissues and organs, and they don't have an immunogenic epitope for another human being, offering superior biocompatibility and clinical efficacy. Ideally, tissue from young, healthy donors are the best source, but human tissues is relatively scarce and its availability is limited, especially for younger, healthier tissues. That is difficult to get it. Cadaveric tissue can be used as donors, but availability and acquisition is limited. Cadaveric skin sold as allodum and graft jacket is used clinically for wound treatment in the modern days. Tissue associated with birth such as placenta, umbilical cord and fetal membrane are often discarded after delivery, making them more abundant and accessible. Hospital after birth, if they are throwing it, if you can collect it, that will be a great thing to have. Studies have shown that ECM derived from placental tissues possess favorable immunogenic and regenerative properties containing various growth factors, example epidermal growth factor, TGF-beta, VEGF, etc. that support the growth and differentiation of diverse cell types. Because it is from a fetus, it is pro-regeneration in any way. So those ECM will be superior than a adult ECM. For instance, research in Murchison et al. Demonstrated that placental ECM hydrogels can serve as a suitable substrate for HIPSCs differentiation into 3 embryonic layers. You can make ectoderm, endoderm, mesoderm. Wang et al. Utilized placental dECM hydrogels to construct spinal cord-like organoids that are more stable and mature than those developed using simple matrigel. So we should understand the embryonic leftover tissues have huge potential. Anyway, we are throwing them. So let us see what are the decellularization methods. This is an overview of common decellularization techniques and post-treatment processes, as you can see here. Decellularization of target tissues is effectively achieved through chemical, physical, or enzymatic methods, with combinations of these approaches often applied to a given tissue based on which organ, which tissue, their strength, the tissue density, cellular density, everything will vary. Accordingly, you have to come up with a strategy. The harvested dECM materials are sterilized to eliminate potential microbial contamination, to reduce the toxicity and enhance the biocompatibility. Inevitably, these processes can impact the structure and functionality of the dECM, which is frequently addressed by employing solubilization and cross-linking methods for improvement. As you can see here, chemical treatments are given, biological treatments are given, and sterilization is applied, and dissociation and cross-linking is applied, physical treatments are applied. So once you harvest the organ, you have to do extensive processes. It can be biological treatment, can be trypsinization, nuclease treatment, and physical methods can be, applying pressure, pulling, pushing, etc. So there are different approaches, as you can see in this cartoon, but they have to be applied for getting a proper dECM prepared. So this is an overview of the application and research progress in organoid and engineered organ based in dECM materials. So the utilization of stem cells and organoids to populate the whole organ decellularized scaffold need to be done if you want an organ, followed by cultivation of bioreactors. It has significantly advanced the field of whole organ bioengineering. So with the rapid progress of these technologies, the researchers demonstrate the immense potential of this application in regenerative medicine and organ transplantation. It offers a promising avenues for addressing current challenges in these fields. So you can see here, there is an injury, cancer, failure, etc. in the patient, and there is a shortage of donors. It's not available, and hence the transplantation is not possible. And the whole organ bioengineering, one option, and bioengineering of organoids is another option. And we have to decide the strategies of bioengineering based on the availability of dECM. That is what you are seeing. It can be from human, cadaver, pig, etc. And you can decide what ECM materials can be used. So ECM materials exhibit tissue and organ specificity and can be enhanced with relevant proteins and cellular molecules to promote developing and constructing organoid models closely mimicking to that of the natural organ itself. So now another example is an application of dECM materials in gastrointestinal organoids and engineered organ culture. One example how you do with this is a complex picture, but don't worry about that. Those who are interested can read this article. Reference is given. First A is the decellularization and characterization of human SI and colon scaffolds. You can see here it's a part of the gastrointestinal tract. And B is a schematic representation of the strategy for in vitro preparation of functional human jejunal mucosal grafts using bioreactor. That simple, get rid of the cells and you inoculate them, provide them the nutrition so that they colonize. And C is the bright field images of the gastrointestinal organoids cultured in the decellularized stomach-derived ECM. So it is also known as SCM, stomach-derived extracellular matrix, or decellularized intestine-derived ECM, IEM. And hydrogels and matrigels are also compared to that of this dECM. And panel D is a schematic diagram illustrating the application of dECM hydrogels carrying GI organoids as grafts for treating acute epithelial injuries in mouse models of the stomach and intestine. So you can use mouse models to make the proof of principle of these animals, and that is what you are seeing here in the panel D. And people use GFP cells so that you can show the newly formed organ has got it has no cells, and or other way around, if you took the dECM from a wild type, you can use GFP expressing cell to show that yes, my cells are staying back, either way one can do it. And if you look further, that where do we stand? If you look once again closely, the organoids that are produced when you take from a donor, if it has got a transgenic reporter line, we can trace the fate of those cells. Sometimes it may happen that the host derived cells may intercalate into these organs, newly placed organ, and this organoid can become a full functional organ. So those tracing work, you will end up getting a chimeric organ. So organoid transplantation, once it is done, it has to be followed precisely. How the donor cells acclimatized, or how the host derived cell got acclimatized. It can also happen sometimes the wandering neural crest or wandering other stem cell population can also contribute. Such studies are extensively done in using various animal models. We cannot do that in humans. So looking into the conclusions and outlooks of this dECM approach, dECM is a designated approach to remove mainly the immunogenic cells while preserving the original tissue architecture and composition. We know that by now that dECM purpose is to have the proper identity of that organ or organoid, whatever you are making. Organoid has to become a proper organ, or if it is a part of an organ, then you don't need to fix the entire organ. Only part of the organ is bad, then you need an organoid only. You don't want the full organ. It's like if your car's tire only has gone bad, you don't need to have a new tire. So tire is an organoid, part of the car. Due to its inherent structure, enhanced bioactivity, reduced immunogenicity, and favorable biodegradability, the dECM has generated a widespread attention in tissue engineering and organ culture field for biomedical applications. And the work is worked out, or this research is worked out mainly in mammalian models. The prevention of, or to prevent the decellularization techniques, the prevalent decellularization techniques most commonly applied are, they use physical techniques, chemical techniques, enzymatic tools, which can be employed individually or in combination, and again depending upon which organ you are dealing with. Currently, dECM derived materials have been increasingly applied in the preparation of organoids, engineering, and other engineered organ. Further research into the specific impact of ECM of different tissues and disease various sources on dECM and subsequent bioengineering is need to be done to enhance organ models, physiological complexity, and clinical relevance. Although we know proof of principle is done, but this approach may not be foolproof in every available scenario. That is why one has to work on this approach to improve the biological acceptability and how easily, just like you manufacture a phone. There is a conveyor belt, there is a assembly line, like that it should reach, so that everyone gets benefit out of it. Despite the challenges in exploring dECM for organoids and engineered organ fabrication, ongoing research and technological advancements bring us very close to creating viable transplantable tissues and organs. We are reaching that stage. These developments include optimizing decellularization processes, refinement of organoid construction methods, scale-up production, and enhancing the matrix biological cues to guide cell behaviors. The continuous improvement of these technologies holds great promise for future organoid engineering and engineered organ fabrication. So, the future of organ culture and organoid is in a very promising track, but lots and lots of researchers have to come into action for getting benefit to the humanity. We will learn more about the regeneration biology in the next class. Thank you.